Hello and welcome back. This is another lecture for simulating neurobiological systems in Systems 556, taught at University of Waterloo in the fall term of 2021. So we sort of reached kind of a point in the course where we've introduced all the core underlying theory for how do we build these simulated systems, and from here on in it's sort of applications thereof. But I want to spend a little bit more time, now that we've identified these sorts of basic components that we know how to build. We know how to build groups of neurons that represent variables. We know how to build connections between groups of neurons to represent computations on those variables, so computing functions. And we've shown that if you add recurrent connections, then now you get to compute differential equations. But what does that all mean? So like from those components, you can build a lot of different things. Like those components, I mean, yes, that's a Turing complete set of components. You can build anything you want. What's practical to build? What's useful to build? Can we get some sort of sense as to what it means to build up a biological system from these sorts of components? So the first part of today's lecture, we're going to do a little bit of an aside and build a brain. We're going to sort of build the smallest minimal sort of thing that we might kind of want to have a little brain do. Okay, I'm just going to build it up using the components that we've seen so far in the course. Okay. And what do I mean by a little brain? Well, at sort of the bare minimum, I want something that has some sort of sensory input, has some sort of motor action output, needs to do some sort of decision making, and has some sort of memory. Okay, so I want all of those things in sort of like the smallest, simplest kind of form. We're not going to be modeling any particular biological system when I go and build up this model, but the intent here is just sort of give a sense of the techniques in sort of their minimal version, if we're going to sort of build something up out of smaller components. Okay. In order to do this, I'm going to make use of the software Nengo that I introduced last time. I'm also going to be making use of the graphical user interface version. So when you use the Nengo software, you can either use it as a normal Python package and go work with it in Jupyter Notebook or wherever it is that you're used to doing Python. But it also comes with a graphical user interface that I find is really useful for doing sort of live interaction, which we're going to want for this model. So you install that with pip install Nengo GUI. It's already installed on this computer. And then in order to run it, I just say Nengo. And what should happen is I should get a browser window that has in it a little model. And the code over here is just normal Python code. It's just a text editor. You could go use your own text editor if you wanted. This is the file that it's editing. And as we go and build up this code over here, it's going to be displayed over here on the left. So I'm just going to start by giving us a totally new file name. So we call this, I don't know, a simple brain. Okay. And what do we want to do with this? Well, I'm going to start by just sort of defining what it is that we want to build. Okay. So, this is a very simple brain that I want to build. And what do I mean by a simple input, simple output, simple memory, simple decision making? The features that I want. So I want the input, some input is sort of, okay, the picture I'm going to have in my head is I want a little critter that, I can tell it where some food is, and it can run off towards that food. But if maybe, like, if things get, maybe if it's dark out if it's dark out, then it's safe to go and explore and find food. But if it's bright out, then hey, you want to go hide. Okay. So there's the decision making. Okay, so I guess we've also got to have an input of is it bright out or not. But then where are we going to go hide? Go back to hide wherever it is that you started from. Okay, so that's where we're going to need a little bit of memory. All right. So my inputs, I've got, what do I mean by what direction his food is? So okay, so we've got something that says how bright. So one input is brightness, and another input is where is food. My outputs, I'm going to have something like direction to move. Fine. And then our sort of our behavior is if dark, go towards food, otherwise go to starting location. All right, so that's sort of a high-level verbal description of what we're trying to do. The challenge is then going to be, how do I get neurons to do this? In order to use the techniques in the course that we've talked about here, what we're going to do is we're going to say, hey, all right, I need to turn this into math, I need to turn this into variables, I need to turn this into functions on those variables, okay, and differential equations on those variables. Cool. All right. How are we going to do that? So I find I normally want to start by, the most straightforward things tend to be inputs and outputs. All right. I've got some sort of thing that represents brightness. Cool. All right. We can do that. So again, whenever working with this Nengo software, we say import Nengo so that Python has access to it. We build a model, which is just, or we build a network, which we're going to call model, which is just all the components that are part of our brain model. And then we're going to define a bunch of things in it. That's where we're going to start with this code. So I need a group of neurons that's going to represent brightness. Okay, that's a variable. We'll call it brightness. I don't know. Or maybe B, I don't know. Is some a group of neurons. Ensemble. How many neurons are we going to have? Well, what is this? So it's brightness. This just seems like this is just going to be like just a one-dimensional value. This is just a scalar. Right. We're going to need some number of neurons. I'm going to do 100 neurons. One common question, of course, is going to be, well, how many neurons do you want to put in there? As we saw in the course, as you increase the number of neurons, your accuracy is going to improve. I generally start with either 50 or 100 neurons, something like that, just because that gets me a vaguely reasonable amount of activity of noise with the default neuron parameters inside Nengo. Again, this would be something where I want to start with something like that, just build my model. If I had some particular biological system I wanted to compare to, then we could go and explore later how to make those parameters fit well. Okay, B, I'm going to forget what that is, so I'm going to call this brightness. Okay, or bright. So I have that. What's one variable? We're probably going to need some sort of external stimulus to let us control that. And we'll just set it to 0, and we'll make a connection from stem bright to bright. There we are. So we have something that will let us make a little slider such that we have some neurons here. Sure, click and spike. Okay, and we've got some external stimulus that as we vary this, we get this neural activity, and we can see, yes, it's the neurons are encoding that information. No big surprises given what we've seen in this course. Okay, I have a group of neurons that are representing that brightness. What else do I want to do? Well, we've got another input. Where is the food? So this may be some sort of sensor that says, all right, relative to me, there's some food at some particular location. Okay. Now we got an interesting question. How do we want to represent that as a variable? In math, there's like tons of different ways you can represent something. I could represent it as an angle and a distance. I could represent it as an xy coordinate, where 0, 0 is where I currently am, and xy tells me where the food is. I could make up all sorts of other things. When I'm dealing with things in math, normally it sort of kind of doesn't matter. Like you can transform back and forth between all those different versions, and you just do whatever's most convenient for the math. Here we're in a situation where the decision we make about, well, what variable is being represented, or how the variable is being represented, can actually impact our model. Right? For example, suppose I did decide that what I wanted is something that represents an angle. So, maybe I want to represent the angle and the distance to the food. Okay. And I, might, so I might say something like, all right, food. I don't know, I've got a few more neurons. It's two-dimensional, right? Because I've got two things I'm representing, an angle and a distance. Right. And we're going to say, all right, right now, there's nothing there. From stem food to food. There we are. Two variables being fed in there. And I'm just going to decide, given what I described there, that okay, I could call this first one, we could call it the distance. And the second one could be the angle. Right? That would be a common way of representing things. But hold on a second, that's a little bit weird here. For one thing, that sort of makes it a little bit unnatural that, okay, well, what if the distance is negative? Well, that's weird. Now we've got to sort of, okay, we'll just never use that. We'll just never put the slider down there. So we'll never do those sorts of inputs to the neurons. But then we get a similar weird thing on this slider here, this one that's supposed to if it was representing angle. Right? Because if I set the range to say -4 to 4, if I feed in, here, let's actually show the value coming out of this. So there we are. Set the range, -4 to 4. Okay. So let's say that there was food at 1 meter away and at some particular angle. Right. And now, of course, one of the things that was sort of commented whenever we're building models with neurons, we need to make sure that these neurons are representing across a good part of the space that we're using. The default in the software is that when we solve for the decoders, we only solve for the decoders across the space a circle of radius 1. This is well outside the circle of radius 1, so we're going to need to increase our radius. That might not even be enough. Its radius might be 5. Okay. All right. So now I might say, all right, there's food 1 meter away at an angle of, I don't know, 3 radians. Right? And cool. All right, it's representing that. I have my neurons, they're representing something at an angle of 3 radians at some distance. Right? We can decode that information fine. But something's a little bit weird with this style of representation here. If this is a distance and an angle, well, if I go up to more than pi, 3.146, right? Well, that becomes the same as minus pi, right? And so that change there, that's so let's say, I don't know, I rotate slightly or the food moves slightly, and so it moves from just under pi to just over pi, so that goes there. What's this representation going to do? It'll work, it'll change, but it'll change smoothly, right? And so that's going to mean that if I chose distance and angle as my two variables that these neurons are representing, then there's going to be some situations where an object's going to move a little bit, right? And then I'm suddenly going to think, my internal representation is going to suddenly think that it is following a very strange trajectory, right? Like this, if I actually, what this would be saying is, okay, there's food, I don't know, sort of directly behind me, and then instead of directly behind me to the right, but then instead of moving directly behind me to the left, it's now spinning around in front of me and then going behind to my left. That's weird. That doesn't seem to be a very natural way of representing a location in neurons. What might more a more natural way be? Okay. Well, a more natural way, it's going to turn out to be, hey, well, we'll just use XY coordinates. Instead of having these two variables be a distance and an angle, we're just going to use XY coordinates, where 0, 0 is right where I am. Okay. And then, okay, oh, there's food at this location, X something, Y something. All right. That doesn't have this weird discontinuity, strange things happening at pi to minus pi sort of problems. It doesn't have this whole, okay, how do you deal with the negative radius problems? The other cool thing is those two choices. So on the one hand, that choice that I make about which way to go, I could think of that as, I'm making this choice because, oh, this is going to have a better behavioral impact because I don't want to have this weird smoothing property. But another thing that does is if we go and look at the tuning curves of these neurons, you can tell the difference between those two choices. Right? And it turns out in biology, whenever we found neurons that seem to be responsive to some sort of location, a 2D location sort of thing, maybe not whenever. One common way that biology represents a 2D location is doing exactly this, right? That you have a two-dimensional input. You have neurons. Again, the neurons are going to have randomly chosen tuning curves in that, or randomly chosen encoders in that two-dimensional space. That's going to mean that there's some neurons that are responsive to one direction, more to another direction, to another direction, to another direction, and so on. And that's exactly what has been observed in biology. So there's a nice sort of coherence between what style of representation seems to be happening in biology and what style of representation is useful when doing this programming and building. All right. That was maybe was a little bit too much of an aside. The point out of that is we have somewhat principled reasons for saying, hey, when I'm going to represent this two-dimensional value, I'm going to represent it as an XY in XY coordinates rather than some other space. Again, you can choose other spaces. It's just going to change what sorts of things you end up computing, and it's going to change your neural properties, and so then you can go test those different things. But for this case, we're just going to bring it back down to a radius of 1. Do that because we're going to remove that. Set the range on this back to -1 to 1. And I will also note that this plot is probably more useful as an XY plot. So, yay, I have some neurons. I can change the stimulus. All right, now it thinks there's food in front of me and a little to the right. And now it thinks there's food behind me and a little to the right. Now it thinks there's food behind me a little to the left. Okay. So far all we've done is represent information. We've just sort of put information in. Those are our two inputs. What's our output? Well, we've got some sort of direction to move, motor action output thing. Let's just do that. I've sort of implied, I guess, that we're in some two-dimensional space. So fine, we'll have dimensions equals 2. There is our motor output. So that is just going to be, all right, as we change this, what's being represented in this group of neurons, that's going to say, you know, if it's 0, 0, we'll stay still. If it's something else, we'll move in those directions. Okay. If we were doing this as a real sort of big model that we were sort of connecting to some environment, right, we would connect up another node that would sort of take this value, the same value that's being plotted here, and say send it off to whatever thing is simulating the environment, or send it off to a real robot to have motor control for a robot, and then the sensors on the robot or the sensors coming in from the simulated environment could be used in place of these sliders to go and control that. Right? And again, because Nango lets you put arbitrary code inside a node, it's relatively straightforward to connect it up. As long as Python can talk to your robot or Python can talk to your simulated environment, it's relatively straightforward to just drop in a function in there and let the neurons go and connect up to that. All right, so we've got our input, we've got our output. But we've now there's this behavior thing, right? And that's really, this is the heart of what the heck's going on here, right? How are we going to make this behavior? Okay, this behavior looks complicated. There's all sorts of options going on here. Let's start simple. Let's just say, look, let's forget this decision making. Let's just go towards the food. What would it mean if I wanted to take the expression go towards the food and turn that into math, turn that into an equation? Well, go towards the food with this style of representation is pretty nice and easy. That's just, well, motor equals food. That's just, if the food is up here, then set the motor to that. Right? And since just the identity function is enough for that, I could just say, all right, connect food to motor. Okay. If the food is up here, the food is to the right, it'll head to the right. If the food is up there, go in that direction. Okay. Again, if it's connected to some environment, then as you start moving towards it, then this would come in closer, and this would come in closer, and this would come in closer, and eventually would reach the food, and it would stop. Right? Of course, we could do other things. We could say, all right, maybe we want to run towards the food faster. Right? I could have said, food func. So this is if I want to do some other function. Right, so maybe m is my variable, or sorry, f is my variable of where the food is, and I might return, I don't know, f times 10, or f times 2, right? Then I'd sort of run towards the food faster. Right. Cool, so now the food, even when the food is just a little bit over, now I'm going to run sort of faster in that direction. Or I could say take f and normalize it, and so that way I'm just always running at full speed, even if the food is right next to me. I could do something like that. Okay. Let's try that one. Import numpy as a p. Return f divided by the log norm of f. Cool. Oh, no. Okay, so now wherever the food is, I'm still running at full speed, but just in that, whatever that direction is. So no matter where the food is there, I'm still running at full speed. That might be, again, these would all be slightly different behaviors, and it's not going to perfectly implement that function. Right? So if I feed in 0, 0, the function, so it hasn't perfectly approximated this function. Whatever it's ended up doing still ends up, hey, if food is right there, stop. It's an interesting sort of side effect of a system like this. Like what the math is actually, if the agent was actually just following that math, then even if the food was like 1 micrometer to my right, I would be running at full speed to my right. That's a really hard function for neurons to approximate. It ends up approximating a smoother version of that function, which ends up having this nice property that, hey, when I'm right next to the food, I stop. Interesting. Right, but let's simplify this just for life, for sanity's sake, and we're just going to stick with the identity function just to start with for now, for our model. Okay. Cool. All right, so that is at least a really simple thing where I'm like, okay, wherever the food is, go in that direction. Fine. I need something fancier than that. I mean, we're going to need more than that in order to deal with this whole sort of complicated behavior thing that we want. Let's start with this go to the starting location aspect. Do I want to do that next? No. Let's start with only do this if it's dark. Okay. So I'm going to start let's trying to implement just this part of it. If it's dark, go towards the food. Okay? So that way I don't have to worry about memory or anything like that. I'm just like, if it's dark, go towards the food. So what does dark mean? Well, we'll say dark means the brightness is less than 0. Okay, just because we're using -1 to 1 for the brightness, so we're going to say dark is less than 0. So I only want to go towards the food if brightness is less than 0. How can I write that as a function? Well, that's sort of what I just said there is a function already. What function is that? If brightness less than 0, then it's whatever value is in food. Otherwise, I guess 0. For now, we'll just say that otherwise it's 0. So that's a function, but it's a function of two things. It's a function of the brightness and the location of the food. So I'm going to need, if there's a group of neurons, if I'm going to have neurons compute that function, I'm going to need a group of neurons that has all of that information together. Okay. So we're going to call this do food. It's an ensemble. How many dimensions is in it? Well, there's 1 dimension for the brightness and there's 2 dimensions for the food. So that's a total of 3 dimensions. Okay. Oh, and what's its radius? Well, if the food has a radius of 1, and the brightness goes from -1 to 1, that means that 3-dimensional vector, that could have a radius of up to like √2. So we'll just sneak that in and give it a little bit more radius. Okay. How do we get the information from these 2 things into there? Well, that's just functions again. So let's say I wanted to get the information from the brightness. So let's say I've got 3 dimensions in here. Right? and I want to have the information from the brightness in as, say, the first of those dimensions. Then I could define, I don't know, we'll just call this func1. It's a function of brightness. Right? I could define that function, and I can make a connection from bright to do food that computes that function. Is that okay? Does that make some sort of sense? Okay, so let's do food now. I'm going to save this. Do food has 3 things in it, one of which is the brightness. Okay, and the other 2 are nothing, and so they're always going to be sitting there at 0 because that's what it's always being fed in there. Okay. All right, that's a function. It's a little bit weird. This sort of function, this sort of rearranging of data and combining data from different groups of neurons comes up a lot when we're building larger systems. So we made a shortcut for it. Okay. So that same thing, because that's sort of like an identity function. It's just a weird kind of identity function, right? If I get rid of that, right? So instead of defining a function, I can write it that way. Okay. So that's saying, take whatever's in bright, put it into do food. If I didn't have that square bracket 0, then I'd get an error. So it's like, well, brightness is 1-dimensional, do food is 3-dimensional. What do you want me to do? But if I say that, then that's saying, oh, you want me to implicitly define the function that is take this value and put it and have it as the first dimension out of 3, right? Define that function, go connect, solve for those connection weights, go connect everything up. Okay. Similarly, I can take from food. Okay. And this is just the standard Python slice notation. This is the same way that Python always uses to refer to matrices and vectors and things like that. So we're just using the same syntax. Okay. So that's saying from the first dimension on, or dimension 1 on. So now what that should mean is that in this population over here, one of those things is encoding the brightness, and then the other ones are encoding the XY location of the food. Okay, all that information is encoded in those 3 neurons. Or not 3 neurons, in this 300 neurons, which are representing a 3-dimensional value. Okay, now what's my function that I want to do to get information out of that? All right, x is now a 3-dimensional thing. I'm never going to remember what those 3 dimensions are, so I always find it useful as the first line in my function to give meaningful names to these variables. So they are brightness, food x, and food y. Right? So that's x is a 3-dimensional thing. Split it up into those 3 values. And now I can just use exactly what I was saying before. If brightness is less than 0, return food x, food y. Otherwise, I still need to say something, otherwise we're going to return 0, 0. Now we're going to make a connection from do food to motor that computes the food function. Oh, and one nice thing of having the fun diagram here is now I notice, oh, hold on a second, I've got 2 different things. Now that I've defined this one, I really don't want that first connection anymore. So let's get rid of that one. All right, does that work? Okay, so let's make it bright, or let's make it dark. Fine. Let's put the food somewhere. Food somewhere. Okay, cool. It's heading in that direction. And now I'm going to make the room bright. Went back and stopped. Looks like it didn't exactly stop. Looks like 0, 0 is a little bit off from where we are there. We might want to sit down and change things, increase the number of neurons, things like that in order to improve that a little bit. It'll turn out that we actually won't need to once we get this a little bit more complicated. But the basic idea is there that, okay, we are now we're making a decision, right? It's still we're just approximating a function, right? I mean, it's a weird function, but it's just a function. And there is this aspect that even though I defined the function that just, even if it was like the brightness of minus 0.2, I should still go towards the food and not stop. And you notice it doesn't do that. It's sort of, oh, all right, it's kind of dark out. I think I'll cautiously go towards the food. It's not going at its full speed. If it was darker, it would go at full speed. Again, not something that's there in this function. That's just a side effect of the fact that I'm using neurons to approximate this function, and they're going to end up doing a smoother version of that function. Okay. Any sharp discontinuities are going to get smoothed away. Okay. And again, if it's really bright out, we'll stop. If it's only kind of bright out, then we're not perfectly stopped. Cool. All right, we've got some sort of decision making going on here. We've got one more step here. Go to the starting location. How in the world are we going to know where we started from? It sounds to me like we're going to need some sort of way of knowing where we are. Can we do that? If I was doing some sort of complicated robot or something, then we might have some complicated vision system that lets it sort of, figure out where it is based on what it can see. That's a whole other, that would be a couple of courses. There's definitely lots of people researching that sort of thing. We're going to do something a little bit simpler here, and that is, well, hold on a second. I know what direction I'm moving. Heck, as a person, if I'm in a room and I close my eyes and I start walking around, I can still vaguely keep track of where I think I am. All right? And animals do that. There's all sorts of studies of how good animals are at doing that. So let's build that into our system. I know what command I'm sending to my motor system. If I would like to use that, if this is my sort of velocity signal, I would like to compute my position from it. What is that function? Well, that's a differential equation. That's an integral, right? That the integral of velocity is position. The other way of thinking of that is, well, if I have a group of neurons that is my position, so new variable, whoops, ensemble, neurons, this is 2, so that's going to be my position. And what I would like is I would like to have it such that if motor is 0, then position is not changing. If motor is sort of something is positive, then that should increase that value in position. If the motor is negative, that should decrease that value. That is computing the integral. From the math that I showed in the previous lecture, you can go and sit down and figure out exactly what functions you would need to approximate in order to get that to happen. And for the integral, it's a sort of a really nice special case. Right? And the rule for that one was, okay, you have some time constant of your neurotransmitter. And one rule of thumb I'm going to use a time constant neurotransmitter that's at the sort of the high end of what you see in the brain, partly because it turns out that integrators are more stable when you do that, and also partly because in the brain a lot of recurrent connections are with these longer time constant neurons. Right, and then the rule is you do a connection from position back to itself, computing the identity function, because the rule was take the part of the differential equation that refers to your current value, multiply it by tau, and then add the identity. And if my differential equation is, d position, d time equals velocity, well, position doesn't show up on the right-hand side. So 0 times tau is 0 plus identity. That's just the identity. And we're going to actually say, all right. Okay, so now all of the connections between these neurons back to themselves are all optimized for making this, for whatever value is being represented inside the position neurons, pass that information back to yourself. That's sort of another sort of more intuitive way of thinking about all that math that I showed before about how to compute the integral for this one special case, or all the math I showed before was for the general case of any differential equation. For the special case of an integrator, you can sort of think of it just in terms of, well, look, all I want to do is I want to pass whatever information I'm currently representing back to itself so that whatever I'm currently representing, if I get 0 input, it should stay the same. And then make another connection from motor to position. And it turns out that you want to have the function, so we're going to use that same synapse, fine. But then the function that we want, I don't know, this func, which was m, it was supposed to be return tau times m. That's what the math said. Again, in Nengo, these sorts of functions are things that I'd come up a lot of, just sort of linear functions. I have some variable, I want to multiply it by something. Maybe the variable's a vector and I want to multiply it by a matrix or whatever. So again, we have a shortcut for defining those sorts of functions. So that's saying, hey, when you do that connection, just do the function multiply by tau. Okay. What should that do? That should compute the integral. The only sort of weird thing to remember is, oh, right, I have to multiply by this time constant. Fine. Okay. So what does that mean? What in the world are these position neurons now thinking? Motor system. Got my position system right here. All right, so let's make it dark out. Okay, let's say go to the right. Okay, all right, well, okay, this position neurons, there's going to be some limit based on the radius. We'll play with that in a moment. But if I say, hey, go to the left, it should start going to the left, and then I can stop, and it should stop. Let's say go up, it goes up, stop, stop. I'm keeping track of my position. Right, we can go diagonally, fine. We can go this way, fine. I have a group of neurons that will store position information. Couple weird things in there. Okay, you will notice there's a little bit of drift. Yep, that's going to happen. I might deal with that by increasing the number of neurons. Oops. That should make it a little bit more stable. And we could do experiments. We could do things, okay, with how many neurons, with what sort of firing properties, how stable would it be, and if I had some real creature, I could go ahead and do some comparisons in order to see, does the model end up being something like what the biology says? Right? How long can it remember information for? We've also got this weird situation where it seems to have, this sort of boundaries. Does that happen? Maybe we just make the boundaries really large and hope that we just never hit them. Does that work? Are there other techniques? Later on in the course, we might talk a little bit more about another possibility of how you might represent spatial information that does have the property that it means that you don't end up hitting a boundary. So there's, again, interesting comparisons there, and that's going to map onto things like grid cells, and there's all sorts of biological stories that we could go ahead and talk about, starting with this as just sort of this core example. Cool. We are representing our position. We have some sort of basic memory in our system. Why did we want to do that? Well, what we wanted to do is we wanted to have a system where, hey, if it was bright out, go back to where you started from. So that's going to be similar to this do food thing, but it's going to be using is it bright out, and we're going to use the position information rather than the food information. So we're all going to need another of these sorts of things that have large numbers of neurons. Or sort of this, we're going to have this other one. We're going to say, all right, hey, do home. Okay, and we're going to feed in the brightness information to one of them. We're going to feed in the position information to the other one. Okay, all right, so what do we got here? Oops, there's this thing here. So now we have this new group of neurons over here. It's getting information from the position and information from the brightness. So it's got 3 dimensions there. Now we can decode out of that some other function like this in order to send to our motor system. So this is my home function. And the 3 things that are in it are the brightness, the position X, and the position Y. And what's this function? Well, if brightness is greater than 0, then we want to, okay, we know what my position is. If I want to head back to where I started from, then I want to return the negative of the position and the negative. There we are. Otherwise, return 0, 0. Connection, do home, do motor, function equals home func. Okay, does that work? Save it, run. Okay, so let's put it in darkness. Head off to the right, off to some location. So I now think I'm at this location. And now I'm going to turn on the lights. And it heads back to its initial position. So show it food. Hey, there's food over here. Totally ignoring the food. Right, position's not changing, totally ignoring the food. The motor's not changing. Turn the lights back off. And off it goes towards the food. Right, put the food over there. All right, fine, it's going over there. Put the food down there. It's going over there. Turn the lights back on, and it heads back to the position. We have built a little tiny brain. Cool. That's, I think, sort of the minimal example of what it means to sort of take an algorithm that I initially described just in words, and try to take that algorithm, break it down into, okay, what are the variables? What am I going to, how do those variables defined? What sort of ranges do they have? What are the functions that I need to compute? And what are the sort of differential equations that might be needed? Right. And as is kind of typical, we generally get this sort of interesting structure, recurrent structure, things connected all over the place. That tends to come up fairly typically when we build these sorts of models. And also similar that you see big messes like that in the brain. There's definitely lots of other sorts of interesting tricks we might be able to bring up and whatnot. And other ways we might optimize it. We might be able to talk about things like, oh, do I really need these neurons at all? Could I reduce things a little bit more? Are there more efficient ways of breaking things down? But I think that gives a sort of an interesting representation of how we might go about building a small, simple little brain by using this breaking things down approach. I'd also say it would be a really interesting, complicated. I've never seen anyone successfully try to use something like backprop or some other sorts of neural network techniques in order to build a model like this. I guess maybe it would. I don't even know what you would even, how you would even set up that training data. I would be curious whether it would be possible to do that sort of thing. I've never seen it successfully done. I've seen people attempt it unsuccessfully. But anyway, my hope is that we've got some indication here of, hey, we're using our techniques to build up a brain in kind of a weird way. Awesome. So that gives a feel for what we can build, but one really important thing, and it came up a few times as we were defining these models, is I ended up doing things like, okay, well, I defined this function, but I got out of it kind of a smoothed version of that function. And that's a sort of a weird aspect of building brain models this way, right? Because I'm defining things in one way, but I know I'm going to get an approximation of that, but that approximation is going to be dependent on my neurons and how many they are and what neuron properties they have. So it's going to be useful for me to have some sort of sense of what, can we have a principled way of saying, hey, given certain neurons, what functions are they going to be good at? And that's going to take us back to sort of the core lecture stuff that I was supposed to be talking about in this thing, is just analyzing the sort of neural representation stuff that's going on here. Okay. So to take a step back from that big, complicated, big model, when we're just looking at things in terms of approximating just one function at a time, what was really happening there? I have a bunch of neurons. Each of those neurons, we're just worried about the one-dimensional case right now. Each of those neurons has some tuning curve in that one-dimensional space. Okay. And then what we're asking, so if this is what the output of the neurons is, then when we solve for the decoders, what we're doing is we're finding some weighted sum of the activities of these decoders such that the output is the function that I want. Okay. And here's a bunch of different functions. Right. So here, right here, is say this is the function f of x equals 1. Right, so that's just output of 1 all the time. It's a function. It's a weird function, but fine. It's a perfectly legit function. All right, so that's saying find me the weighted sum of these curves such that no matter where I am on this x-axis, my output is a 1. Cool. All right, that's doable with pretty small error. Right, what if I do f of x equals x? So, okay, this is the identity function. This is the thing that we started with right at the very, very beginning. Right, find me a weighted sum that does that. Cool, all right, it's a different weighted sum, so different decoders. And we do a pretty good job with, some error. X squared, same thing, but a little bit more error. X cubed, a little bit more error. X to the 6th, even more error. There's something systematic here. This is sort of giving us a hint of, can we sort of have an understanding about what functions are easy and what functions are hard for a system to approximate. Interesting. So how can we go ahead and sort that out? Another way of phrasing what we're asking here is, I have a bunch of things I want to do weighted sums of, and I want to know what things they're good at making. There's another name for that. And depending on what sort of linear algebra courses you've taken, that might be jumping out at you. This is principal components analysis. This is singular value decomposition. Right? If I take a bunch of curves, right, and I do singular value decomposition on that, that's literally what that's doing is it's telling me find the things that if you add together weighted versions of them, you do a good job of building these things up. And I can find out, okay, what are the top singular values? So I can take these curves, I can do singular value decomposition. Okay. And what that's going to do is that's going to tell me what are the things that I'm best at, what are the things that I'm second best at, what are the things that I'm third best at. Okay. And the magnitude of that singular value is going to say, well, how good are you at recovering those sorts of things? This is what singular value decomposition is. If we go and do that for this particular set of tuning curves, so this is a set of tuning curves from leaky integrate and fire neurons with the same sort of, all right, have x-intercepts all over the place and y-intercepts, and maximum firing rates in some range, right? This is the set of principal components that we get. So this is telling us what are the things this is best at. Okay. And we get some lines in there. So each of those lines that I'm drawing, I'm just drawing the first few of these because this is sort of indicating, this graph over here is just indicating when you take these curves, find me the principal things that they're good at representing. This is saying how quickly that drops off. Right? So this first one, it's going to be really good at. What is that first one? I'm pretty sure that first one is this line here. No, it shouldn't be. It should be... actually, I don't think I'm drawing that one. There should be one sort of vaguely constant looking one. The next one is this line here. All right, that's the thing. One of the things that this group of neurons is really, really good at is approximating y equals x. Okay, this is why the identity function is so easy for these sorts of neurons to represent. It's if you do singular value decomposition on those curves, one of the top singular values is that y equals x, something a lot like that. Okay, what's the next one? That looks a lot like x squared. Right. What's the next one? X cubed. No, not quite x cubed. It's some sort of quadratic with two curves. Right. Maybe some people might recognize that particular curve. Doesn't really matter, but it's still we're still getting these more and more wiggly lines. This is our way in to sort of saying this is the set of class of functions that this particular group of neurons would be good at approximating. Right? Cool. But then, of course, once we know that we can do this, well, now we can go about changing our neuron properties and finding out how does that change what things those neurons are good at doing. So, for example, I could switch my neuron model. Okay, I can switch my neuron model to these much straighter lines. Right, this is the rectified linear unit neurons. Right. And again, I'm getting a very similar sort of, I'm still good at the identity function. Right. Still good at, and then we've got these sorts of gradually increasing quadratics as my other ones. Right. They're pretty similar. Right. Also an indication that we're probably, that there isn't much in terms of representational capacity, in terms of, hey, will my neuron models, if I'm using this approach to approximate neurons, should I use a leaky integrate and fire neuron model or a rectified linear unit model? This is sort of indicating that for a lot of functions, there really isn't much difference in terms of what it is that those neurons can do to work together to approximate. As I sort of noted, for some people, and so it's less noisy there, perhaps it's a little bit better with this one, Some people may recognize those curves, right? That one. It's not x squared, x cubed, x to the fourth, x to the fifth. Instead it's pretty close to the Legendre basis, which are just, instead of x squared, it's like x squared minus x or something. Like they're just polynomials, but sums of polynomials. But instead of being the normal polynomials, they are an orthogonal basis. But it's the orthogonal version of the polynomials. Okay. Again, what does that mean? That means the class of functions that either of these sorts of neurons are going to be good at approximating is the class of functions that are well approximated by low-degree polynomials. Okay. Another way of phrasing that is if I have a function and I can do a good Taylor series approximation of it with relatively few terms, then my neurons will be good at approximating it. Some of those ways of phrasing it might be useful. I find the very non-math way of thinking about it is, hey, as long as the function is smooth, my neurons are going to be good at approximating it. That's often what we mean by smooth, is these sorts of things that that you generally get out of polynomials, and then of course as you have more neurons, these can get wigglier and wigglier and wigglier. Oh yeah, fine. There's the actual equation for the polynomial basis, or for the Legendre polynomials. But conceptually, that's the basic set of them. Okay. So that's the ideal math version. This is what falls out of my neuron models. All right. What's some other sorts of questions we can ask? Well, when we look in biology and when we're creating our neurons in our models, we tended to randomly generate this maximum firing rate. Why? What if we had neurons that all had the same maximum firing rate? Right? What's that ending up doing? Interestingly, that mostly just seems to reduce our singular values a little bit. So it actually makes it slightly worse at approximating higher degree polynomials. Right? Might be fine if you're just trying to approximate the identity function. You want something a little bit more complicated, you might get a little bit worse with that approach. And again, in biology, we just generally don't see that sort of perfect control. I mean, originally when we were randomly generating these things, it was just because, well, I don't think biology has some nice way of making sure every single neuron is exactly the same firing rates, or exactly the same maximum firing rate. But also you don't want it to. So that's another thing we can do. Another thing we can do is, instead of randomly generating these x-intercepts for each neuron, we could perfectly space them. Okay? That actually slightly increases our singular values. Right, so that makes it slightly better at doing these higher level things. The trade-off, of course, is now I would have to postulate some sort of biological mechanism for really nicely spacing these intercepts. Maybe some learning process could do that, something like that. I feel a little bit safer just saying, all right, we're randomly generating intercepts, just because, that feels a little bit better, a little bit more biologically plausible. But I think stories could be made either way. You can also go ahead and do something like, only have intercepts in certain ranges. That does horrible things to your singular values. That's going to mean you're going to have great difficulties doing lots of different functions, which kind of makes sense, because if you only have intercepts in this range, then now all of a sudden this whole part of the space over here, everything's linear. And so if everything's linear, you're going to have difficulty approximating things that are nonlinear. Other fun things can we do here? Different looking tuning curve, don't have curves that cross the x-axis. That can be kind of good. That, of course, has this really weird side effect. If you have tuning curves that don't cross the x-axis, every function you approximate is going to have 0. If you input 0, you're going to have 0 out. right? If the class of functions you're wanting to approximate has that property, that can be a nice way of modifying my tuning curves to make that happen. Of course, we can do more complicated things, like what Gaussians, actually. If we do have Gaussians, it turns out if you do this math and you go analyze those principal components, anyone recognize what's coming out in there? Yeah, that's the Fourier basis, or something pretty similar to the Fourier basis, if we did really complicated, bizarre tuning curves. Similar principle is going to happen in multiple dimensions. All those plots I was just showing were one-dimensional, but if I do the similar thing for two-dimensional, well, now I'm going to have two-dimensional principal components. So again, this is going to be what are the things that the neurons are really good at approximating? Well, one thing the neurons are good at really approximating is just the function where no matter what x and y are, the output is the same. Fine. Another thing it's going to be good at approximating is, a function of just one variable and a function of just the other variable, slightly rotated. There's no reason for these things to be perfectly aligned to the x-axis, but it's always going to be the case. It's going to be good. One thing it's going to be good at is a slope in one direction, and then a slope 90 degrees from that. That's going to fall out. And then the next thing that's going to be really good at are the quadratic terms between them. Right? It's going to be good at approximating x1 times x2. X1 squared, x2 squared, rotations of those things. So all that's pointing out is this same principle of, hey, we're going to be good at approximating things that look kind of like polynomials, and the higher the degree of the polynomial, the worse we're going to get. That same principle applies in higher dimensions. And importantly, whatever your neuron model is, whatever your tuning curves are, you can use this approach of just, all right, generate those tuning curves, do principal components analysis, go plot the singular values, and you can see this is the sort of functions that these neurons are going to be good at approximating. All right, so that gave sort of a whirlwind overview anyway of how we might go ahead at analyzing what sorts of functions, and then once we get a sense of knowing what functions we're good at, I think that helps sort of give us a good basis for doing the sorts of things I was doing at the beginning of the lecture of building up a big giant model out of functions. And then any time when I'm doing that, building up a big giant model like this, and I'm going ahead and defining a function, I need to keep the stuff that I just talked about in mind, that, all right, this is not going to be well approximated by a low-degree polynomial. And so it's going to end up doing something smoother than the function I've specified there. Is that okay? If it's not okay, I either need to drastically increase my number of neurons, or I'm going to need to rethink my equations, rethink how I'm breaking things down, until I've got functions where it is okay. It's a similar sorts of process that I talked about at the very beginning when I was like, oh, should I represent things in terms of x and y, or in terms of angle and distance? Okay, those sorts of transformations can really help. All right, cool. So that's our general idea for today, and have fun with that. And I hope that gave a little bit more sense as to how you go about using this stuff practically. Thanks, and we'll talk to you later.